Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in chapter 5. In the figure, the mass of the string is negligible. The pulley is frictionless and there is no friction between M2 and the wedge. The numerical values are M1 equal to 1.8 kilograms, M2 equal to 6.4 kilograms, and theta equal to 50 degrees. A. Draw free body diagrams of both objects. To draw the free body diagram, first we choose the coordinate axis. For mass M1 we have, and for mass M2 the natural coordinate axis is. Next, we represent mass by a dot. As you notice, each mass sits at the origin of its own coordinate system. Then we draw all forces on the body. First of all, we draw the gravitational force on each body. For mass M1 we have, and for mass M2 we have. Now for mass M2 it is suitable to decompose this force into x and y components as the following. As you see, we write only the magnitudes of these components and it is not necessary to use vector form here. Secondly, we draw the normal force perpendicular to the surface if there is a contact with any surface. In our example, only M2 is in contact with the surface, so the normal force is drawn to be like this. Finally, we draw the tensional force for each body like this. At this point, it is important to note that the tension, that is the magnitude of the tensional force on the same string, is the same everywhere on the string. However, the direction of the tensional force on each body have to be drawn different. As the last step to draw the free body diagram, draw acceleration vectors separately. Here, if you calculate, m2 times g times sin theta is greater than m1 times g. Therefore, the motion is like this. However, if you cannot guess the direction of motion, just choose an arbitrary direction. After solving the equations of motion, if you find negative acceleration, then you will decide that your previous choice of the direction of the acceleration was wrong. Then, just change its direction. Okay, these are the free body diagrams of both objects. Let us solve part B. In part B, we find the magnitude of the acceleration of the objects. To solve this part, we need to write the equations of motion for each object. In other words, we use the Newton's second law, namely F net equals m times a. For mass m1, for the correct result, we take the direction of the acceleration vector as positive. Then the magnitude of the net force becomes T minus m1g, which is equal to m1 times a by the Newton's second law. Here, as you see, there is no motion along the x-axis. For mass m2, since we have a two-dimensional motion, for the motion along the x-axis, we choose the direction of the acceleration vector to be positive. Then the net force along the x-axis becomes m2 times g times sin theta minus t, which is equal to m2 times a because of the Newton's second law. Also, since there is no motion along the y-axis, we take the acceleration as 0. Then, by the Newton's second law, we get n equals m2 times g times cosine theta. Anyway, if we add these two equations side by side, we get if we insert the numerical values into the corresponding places, we obtain A as 3.7081 meters per second squared, or approximately 3.71 meters per second squared in three significant figures. As you see, the result is positive, so then we say that the direction we have chosen was correct. In part C, calculate the tension in the string. It follows from equation 1 that T equals m1 times A plus G. If we substitute the corresponding numerical values into this equation, we obtain approximately 24.3 newtons. Okay, this result brings us to the end of the discussion of this problem. Thank you for your attention. See you in the next video.